Happy New Year, kids. Glad to see you, sort of. And today we are going to learn about Green's theorem. Green is a fairly modern mathematician. I think he's English, and I don't remember exactly. I could look him up. But I want you to remember before break, we were doing line integrals. And one of our special line integrals was as a vector field around a simple closed curve. And remember, closed just means, simple and closed means that you have a loop that's closed, and simple means that you don't cross like that, right? You don't have your boundaries don't cross. That's not simple. And closed, not closed, would be something like that, which we did line integrals, right? We computed line integrals of a non-closed curve. But if you have a simple closed curve, we did a special line integral of the dot product of the position direction dotted with the direction of motion, and we got total circulation around the curve, the boundary, right? This boundary. But of course, this was dependent upon F. Remember, we had to parameterize this. Your curve had to be parameterized, right? And you had to have your, right, you had to have your direction of motion or be able to find it. So we did that both with closed and non-closed. When we closed it, we called it circulation, and we used this special symbol with our single integral. We'll also recall, oh, here's a picture, right, of here is a simple closed curve, and picture you on a boat, you're rowing, right? So you're rowing here. This is the path that you want to follow, but underneath, right, your water and your currents are doing different things. So you want to know what is the total circulation around this path given the vector field that's underneath. And remember, we talked about if the dot product is positive, then the flow is helping you as you're rowing. But if it is negative, the flow is impeding your progress, right? You have to work harder. And we talked about line integrals being work, and just with circulation, working around this line. That's what our integral is telling us. We'll also recall another thing we did before break was curl, right? And remember what curl did. Curl was a number, right? It was a number that indicated the circulation at a certain point. What did Tejas call these? Jennies, right? So like if you dropped a little propeller, a little helicopter thingy that I call them, or jennies, right? And if you dropped it in there, what would they, right at this particular point, is your little jenny spinning in a counterclockwise direction? Is it spinning in a clockwise direction? Does it not spin at all? Does it just move with the current, right? So it doesn't spin at all. Remember, we had curls that were equal to 0. And I gave you a formula for the curl, right? It was the partial of the second piece with respect to x and the partial of the first piece with respect to y, right? Because we had our I and j's, right? Given that our vector field was some P in terms of x, y, I plus Q in terms of x, y, j, right? Well, imagine that we dropped a lot of little jennies in here. I do hope that's the right word. Imagine we dropped a lot in here, and we computed the curl of every single one. What Green proved is that if you did that infinitely, all along and even on the boundary, and you summed up those curls over the area, right? Each one of those little rotations, their boundaries around, their inside boundaries would cancel out, and you would be left with the rotation around the boundary. That's pretty deep. Ha, pun intended, deep with the water, get it? That's what Green proved, that the circulation that you get around a simple closed curve, total circulation, is the same as a double integral, where you are summing curls over the area. Crazy, right? Remember, the line integral, the single line integral that represented circulation, was a dot product of your position vector with your direction of motion vector, right? And then we summed them all up and we got the total fluid rotation around the curve of the region, circulation. What green showed is that you get the same value if you sum all of the rotations at every point, all of our little jennies, over the area that the curve encloses. Crazy, right? Move this up. You get the same thing. That's the power of Green's theorem. So why would I want to use green? Well, remember, a line integral depends upon the fact that you can parametrize, that you have this vector, position vector, and that you can dot it with your, right, your direction of motion, your change in x and your change in y. Green showed that you can just sum the curls, and dx dy, you can just write, that is the area here. So remember, this is a dot product. So when you do a dot product, you're going to get your P portion of your position vector dotted with the horizontal change, and then the Q portion, the J, right, the vertical, dotted with the vertical direction of motion. But you would get the same answer by computing the curl and the double integral with the curl. So let's try. Let's evaluate this line integral. This line integral is circulation, so that's telling you that C is a simple closed region. And what green asks you is your region complicated? Is the expression for the curve nasty? And if it is, look at how you might do curl. Is it easier? Then you might want to use green. So this first example, I'm going to do it without green first and then with green. Because as you can see, here's now remember what this came from. This originally looked like this. Right, this was x minus y I and x plus y j, all dotted with my motion. So I did the dot product, and that's how I ended up with this, right, after the dot product. And my region is simple. It is just a circle, has a radius of 2. So let's do this directly, which means first I have to parametrize the curve, right? Well, the circle with a radius 2 is not too bad to parametrize, right? 2 cosine t and 2 sine t. And then notice I need just dx and dy. So dx dt, and then multiply both sides by t. dt is how I got negative 2 sine t. dt and dy dt was 2 cosine t, and I just multiplied through by dt. And here is going once around the circle is 0 to 2 pi. Then I'm going to integrate. So integrating this, then what does the integral look like? Zero to 2 pi of x minus y dx plus x plus y times dy I'm going to bring that up here. I'll trust you to do that algebra, but I end up getting, when I'm done very nicely, oops, I get -4 cosine sine and I hope you can see that these two terms go away. Factor out the 4. Sine squared plus cosine squared is just 1. So I end up just integrating 4 dt. Which is 4t from 0 to 2 pi. Which equals 8 pi. Right, and my curl is positive, so I must be going around counterclockwise. Right? That wasn't terrible, but I did have to parametrize the curve first. And my algebra worked out very, very nicely, right? So it wasn't so bad. But look what happens when I use green. With green, first I differentiate and substitute. Now remember, with green, this is on P and this is my Q. So partial Q, partial X is what? 1. Partial P, partial Y is -1. So Green's theorem says that the line, the circulation line integral will be the same as 1 minus -1 double integral over dx dy, the area. So this is just 2 dx dy. But remember, this is just dA. I don't actually have to integrate this because what is the area that I'm integrating over? What is it? It's a circle, right? So this becomes 2 times the area of a circle with a radius of 2 and ta-da, I get 8 pi. Thank you, green. No parametrizing. They're super nice. So hopefully you see there that even though not using green was okay, there's going to be times where my P and Q are gross, like the next example. Look at my P and Q there. You want to parametrize that? Right? Parametrizing this wouldn't be terrible, but hello? Right? What the heck? Now remember, my dot product is already done. So this is P and this is Q using green. Green says the line integral is equal to the double integral of the region, which is dx dy, right? And I just need to calculate the partials. So what is partial Q partial X? Partial Q partial X, what is that? Well, that's just 1, isn't it? What is partial P partial Y? -3. So once again, look at what I'm doing here. This is just 4 times the double integral over the region. And what is my region? Circle with a radius of 2. Thanks, green. Sweet. So given that underneath the force field under this circle is described by this vector field, this is the circulation around the path, the work I'd have to do around the path. Let's do another one. U. C is a closed path bounded by the positive x, the positive y, and the oh, what the heck? I think I need to draw this. All right, so I'm bounded by the positive x, the positive y, and 1 minus x squared. Okay, so that's my region. Now there is a vector field underneath of this described by P and Q. And I want to know, going counterclockwise, what's that line integral? So again, green, thank you very much, said that the line integral over that curve is the same thing as the double integral over that region of my partials. Partial Q, partial X is what? Two XY, is that what you get, right? Partial Q, partial Y. I'm sorry, partial X, you gotta take the derivative, right? How about partial P, partial Y? What is that? Negative, right? So this isn't as simple as the other ones that we've done. My region is in a nice little circle, so I'm actually going to have to take my dA and look at how would be nicest to integrate this. Remember from way back, I don't know what unit, we need to decide what kind of strips we're going to go. If I have X and Y, right? What kind of strips is that? That would be horizontal strips, right? That would be these strips. Not terrible, but since I already have my function Y is in terms of X squared, right? Maybe I'll go ahead and switch this around. And do dy dx. And then those are my strips through my area. So my X bounds are going to go from what? Good. And how about my Y bounds? Okay. And now I'm down to chapter, I don't know what, 13 maybe, that we did. And I just have to do this double integral. So let's do this piece first, right? We can't separate it out because we've got too many, right? We've got things mixed up together. So I'm going to have to integrate this with respect to Y. So I'm going to get Y squared over 2, which is going to leave me with 2xy squared, evaluated at 0 and 1 minus x squared. So of course, if I put in 0 for y, that part's going to go away. So I'm just going to end up with my single integral from 0 to 1 of 2x times 1 minus x squared squared dx. Well, what do you want to do here? I could expand all this out, I guess, if I wanted to, but I think I'm going to go ahead and use u substitution and just say u is equal to 1 minus x squared right. Let me do some erasing here so I can give myself some room. Right, so I'm just going to end up with a negative. This is my u is getting squared. There's my dx, except for this negative, so I'm going to get 1 minus x squared cubed over 3. And that's going to be evaluated at 0 and 1. So that's going to be negative 1 in here. 1 minus 1 squared is going to be 0, right? Minus, now put in 0, and I get 1 cubed, which is 1 over 3. So negative 1/3 is 1/3. Thanks. Okay. So Green's theorem, a way to take a line integral that is circulation. So Green does say that you need your simple closed path in order to do this. And that instead of computing the line integral, you can instead compute a double integral of the curl of all the individual curls summed up over the area of the region. Okay, I hope that was super fun, and I will see you in our next live session.